Have you ever stopped to think about how the wild, chaotic electricity from your wall gets turned into the steady, reliable power that your phone or laptop actually needs? Well, that's the journey from AC to DC, and it's a pretty incredible process that happens inside almost every gadget you own. So today, we're going to trace that power's journey step by step.
Okay, so this diagram right here is basically our roadmap. Over on the left, you've got that messy AC power coming in from the wall. It then flows through a few key stages, a transformer, a rectifier, a filter, and finally a regulator, before it comes out as that clean, stable DC power for the load, which is really just a technical term for your device. So let's follow the electricity as it moves through each of these crucial spots.
So here's what we'll cover. We'll start with the AC/DC challenge itself. Then we'll get into the real star of the show, the bridge rectifier. From there, we'll actually follow the current, see how a filter smooths everything out, and then, check out the final result.
Okay, so first things first, why do we even need to do this, right? Why can't our gadgets just plug in and use the power straight from the wall? You see, it really boils down to this fundamental difference. On one hand, you have alternating current, or AC. It's that wavy line, always flipping its direction back and forth. Now, that's fantastic for sending power over huge distances to get to your house. But all our delicate electronics, your phone, your laptop, they need a super steady, one-way flow of power. And that's direct current, or DC. So our whole mission here is to turn that wild wave into a flat, steady line. Okay, so how do we actually force that current to stop switching directions? Well, that's where the first and maybe the most important part of our power supply comes in, the rectifier. A rectifier, in simple terms, is like a traffic cop for electricity. It sees all this current moving back and forth, and it basically stands there and directs it all down a one-way street. And the most common, and frankly the cleverest way to do this, is with what's called a full-wave bridge rectifier. And here it is. This is the hero of our story. It's made of just 4 simple components called diodes. You can see them labeled D1 through D4. And it's this special diamond-like arrangement that's the real genius here, letting it sort out that messy electrical flow. So what is a diode anyway? The easiest way to think about it is like an electronic one-way valve or a one-way street. Current can flow through it super easily in one direction, but if it tries to turn around and go the other way, nope, the door slams shut. And this simple one-way rule is the secret ingredient for the entire rectifier. All right, so we've got our AC wave, right, with its positive half and its negative half. What happens when that wave hits this setup of 4 one-way gates? Let's trace the path of the current. Okay, let's start with the positive half cycle of the AC wave. Okay, so during this positive pulse, watch where the current goes. Because of how they're facing, only diodes D1 and D2 are forward biased. That's just a technical way of saying they open up and let the current through. D3 and D4, meanwhile, are like closed gates. This forces the electricity to flow through our load, our device, in one specific direction. All right, but what about when the AC current flips for the negative half of the cycle? Now this is where the magic happens. When that current reverses, the other pair of diodes, D3 and D4, spring into action. They open up, while D1 and D2 now block the flow. But look closely at the path. The circuit is designed to redirect that flow so it goes through the load in the exact same direction as it did before. It's so clever. And here's what we get out of it. If you look at that total output waveform, you can see what the rectifier did. It basically took the bottom negative half of the AC wave and flipped it upside down, making everything positive. So now it's technically DC, right? It's only flowing in one direction. But look at it. It's this bumpy, pulsating DC. And that's still way too rough for our sensitive electronics. Okay, so we've successfully wrangled the current into a one-way street. That's a huge step. But our next job is to pave over all those bumps. And this is where the filter stage comes into play. We've got this pulsating DC, that how in the world do we get rid of all those ripples? How do we turn that bumpy road into a smooth highway of stable power? Well, the answer is actually a surprisingly simple component. The solution is something called a smoothing capacitor. And honestly, the best analogy for it is a small, incredibly fast-acting water tank. When the voltage from our rectifier is rising, that's the peak of the bump, the capacitor stores up energy, just like a tank filling with water. Then, as the voltage starts to drop into a valley, the capacitor instantly releases that stored energy, filling in the gap. It just smooths everything out. And you can see exactly where it goes in the circuit here. That smoothing capacitor, that C,
gets placed right after our bridge rectifier. This perfect placement lets it charge up on the voltage peaks and then discharge to fill in those valleys, smoothing out the power before it ever gets to our device, the load.
So what's the actual result? I mean, how much of a difference can one little capacitor make? Well, the effect is pretty dramatic. Check this out.
Yeah, this really tells the whole story. On the left, you've got that raw, bumpy DC coming straight out of the rectifier. And on the right, wow. After the capacitor has done its job, you can see a much, much smoother, more stable DC voltage. Now, it's not perfectly flat. There's still a tiny little ripple left. But man, what a huge improvement.
So let's go back to our roadmap for a second. We started with that wild AC power from the wall. The rectifier, our traffic cop, forced it all to go in one direction. Then the filter, our little water tank, smoothed out all the bumps. We've just navigated the two most critical stages of this whole process. That very last step you see, the IC regulator, that's like the final polish, a precision tool that dials in the voltage to the exact level the device needs.
So we've managed to tame the wild, alternating current from the wall and turn it into this steady, direct flow. But think about this. What would happen to your phone if that final IC regulator step just failed? You know, while that last regulator provides the delicate finishing touch, it couldn't even begin to do its job without the heavy lifting from the rectifier and the filter that we just walked through. Together, they perform this amazing conversion that literally powers our entire digital world. It's this elegant journey from chaos to stability that happens billions of times a day inside every single charger and device we use, totally hidden from view.